There's a lot to go over. So this test is going to be on some of Section 2 and all of Section 3. So I'm going to go over aromaticity and Huckel's rule that goes along with that. EAS reactions, that's nitration, halogenation, alkylation. And then getting into Section 3 with your functional group, you have amines, alcohols, their reactions, phenols, ethers, ether synthesis, carbonyl compounds, carboxylic acids, and esterification. And that should cover pretty much everything. So first thing is aromaticity. And you check to see if a compound is aromatic by using Huckel's rule, if you remember that. So basically, all you do is count Okay, can you hear now? Okay, my video. Can people online hear now? Please say yes, please. I can't do this right now. Oh, praise God. Okay. All right. Okay. I don't know why I turned off. I literally had my mic on. It just randomly turned off. Okay. Y'all have to watch that for me, because if that happens again. Okay. So if the number of pi electrons fits into the formula 4n plus 2, where n is equal to a whole number, then the aromaticity, and then it is aromatic. So in this case, I'd have 4n equal to 4, n is equal to 1, which is a whole number, so it is aromatic. Okay. And in this case, again, you can count the number of pi electrons by the double bonds. So I have 2 double bonds, 2 pi electrons each, so that'd be 4 pi electrons. Or you can count the number of carbons, so I have 4 carbons. So if I try to put this into 4n plus 2 is equal to 4, then I have 4n equal to 2, n is equal to 1/2, which is not a whole number, so this is not aromatic, which is what we call anti-aromatic. So aromaticity just means that the compound has an unusual stability. So its reactivity is comparable to alkanes instead of alkenes. And that's because of the conjugated pi bond system. If you remember that, it's just where the pi electrons, instead of staying in these like set double bonds, they actually delocalize to the whole ring. So because the electrons have more space to spread out, the energy is lowered, so it's more stable. Okay, so because aromatic compounds have all those pi electrons, they're electron rich, so they can act as nucleophiles, which means they can donate an electron pair. So they're nucleophiles, so they can react with electrophiles, which are electron pair acceptors, which are typically positively charged, or at least partially positively charged. And these are your nitration, halogenation, and alkylation reactions. I already wrote out these mechanisms to save a little bit of time, because we've done these before. So in these reactions, they're substitution reactions by nature. So in nitration, you start with benzene in this case. And the source of a nitro group, which is this right here, in nitration reaction, I hate it too. That's why I went in the other room.
I can go see if they're done in there.
They're not.
Okay.
Look them out, Lydia.
I might. I didn't have time to kick them out. I should have, though. I should have just been a Karen. I should have done it. Okay. So the mic keeps turning off. I'm sorry, but just somebody keep an eye on that and tell me if it turns off again. So your product, you add a nitro group to the benzene ring, and you also form water. I should be a Karen, honestly. So the first step of the mechanism, nitric acid as is not an electrophile, so I need to make an electrophile to add it to the ring. So this is nitric acid right here. So I'm going to protonate that OH group on nitric acid, and then that bond will break right here. So I'll form nitronium, that's that ion, and water. So this nitro group has a positive charge, so it's an electrophile, so now I can add it to the ring. So I have my ring, and my air is going to come from the pi electrons in the ring to the nitro group. And I'll add a nitro group to one of those doubly bonded carbons, and a positive charge will form on the other carbon because I broke that double bond. So this carbon does not have enough bonds, which is why it has a positive charge. And this is a benzenium intermediate. That's what this is called. This is basically a carbocation by nature, but it's formed from a benzene ring. So I have that nitro group added to one of those carbons and a positive charge on the other. And all of these carbons have hydrogens on them already. So what's going to happen is this hydrogen on this carbon where I added the nitro group, this CH bond is going to break, and those bonding electrons from that CH bond will go back to this CC bond domain and to reform a double bond as well as neutralize this positive charge. Okay? So here I reformed my benzene ring, and I have my nitro group added, and then I also released a hydrogen ion, which was our catalyst that we used here. Mm-hmm. Sorry, what is it?
Could you explain the positive charge of the benzene?
Mm-hmm. Yeah. So in this step, I broke this double bond. Okay. So when I break this double bond, this nitro group is added to this carbon. Okay. So this carbon has enough bonds, but this double bond broke. So this carbon, I didn't add anything to it. So it only has 3 bonds right now. So it doesn't have enough bonds. So it has a positive charge.
So does it mean that it has less electrons?
So it would have, yeah, it has 1 less bond than it should. Does that make sense?
So I guess I'm thinking of it like electron, like metals when you get electrons, it compose.
Yeah, so this would have 1 less bond, so it would have less electrons.
Oh.
Okay, so less electrons is a positive charge, right? Does that make sense? Okay, so this is just like a normal carbocation, except it comes from benzene instead of just a regular carbon something. Okay, so move on to halogenation. And these also require a catalyst. So in these reactions, again, you start with your benzene ring or some other aromatic compound. You can add either Br2 or you can also add Cl2. And you'll need to have this catalyst, so either aluminum bromide or aluminum chloride, to form bromobenzene, chlorobenzene, and HBr, HCl. Okay. So in this case, again, I have to make an electrophile because this in and of itself is not an electrophile. So I need an electron to be able to add it to this ring. So I have my bromine. They're bonded together, and each bromine has 3 lone pairs of electrons. One of those lone pairs will come and attack this aluminum here and form a bond between this bromine and this aluminum here. And when it does that, a negative charge forms on aluminum and a positive charge forms on this bromine. So then this bromine to bromine bond will break, and these bonding electrons will go to aluminum. Okay? So this bromine will switch to this aluminum. So I form a Br plus and then Al Br4 minus. So I form an ionic compound. But I really want that positive charge on that bromine, so I can have an electrophile.
So once again, what does the positive charge on the bromine?
So that means it's an ion. Yeah, I don't know how else to. Yeah. So when it's bonded to aluminum, it's gonna have a positive charge. I don't know how to explain it outside of that. I don't quite remember all that inorganic stuff from Chem 1. But just know that it has a positive charge in this compound. So from this ring, the pi electrons from this double bond will come and attack that positively charged bromine. Okay. So I'll add the bromine to one of those doubly bonded carbons, and then a positive charge will form in the other one. And this is a benzenium intermediate again. Okay. And similar to the last one, this CH bond will break. These bonding electrons will go in between here to reform that double bond and to also neutralize that positive charge. And then this hydrogen will bond with one of these bromines to form HBr, and then I'll reform the catalyst. Does that make sense? Okay. So the next one is alkylation. To my knowledge, he didn't want you to know the mechanism for this just yet, because we are going to come back to that. But the mechanism is pretty similar to halogenation. You use the same catalyst as halogenation, but in alkylation reactions, it's a way to add an alkyl group to a ring, to an aromatic ring. So you use an alkyl halide. Where's my pen? An alkyl halide to do that. And the end product, you just add this alkyl group to the ring, and then that hydrogen you replace with the alkyl group will bond with the halogen, which can be chlorine, bromine, or iodine. And I don't think he'll test you on the mechanism, at least, to my knowledge, but he might ask you about the products. Okay, so now to section 3. We're starting with functional groups. So the first one is amines, and this is straight from one of my other study sessions, but and he won't test you on all of this, but some of it will be important at least. So amines are derived from ammonia, which is NH3, and as long as the nitrogen is bonded to 3 other things, the nitrogen will have a lone pair of electrons. Okay, so the amines can be classified as primary, secondary, tertiary, or quaternary, and that depends on how many carbons the nitrogen is connected to. So in this case down here, this is methylamine, and this nitrogen is bonded to 1 carbon, so this would be a primary amine. And this nitrogen has a lone pair of electrons. Probably the most important thing about amines is their ability to hydrogen bond. They could form hydrogen bonds with other amines other amine molecules and water. So nitrogen is more electronegative than both carbon and hydrogen. So they have polar bonds. So it's more electronegative, so it's grabbing the electrons towards the nitrogen. So all of these nitrogens will be partially negatively charged, and the hydrogens or carbons will be partially positively charged. Okay, so in this case with ammonia, these are both ammonia molecules. This nitrogen, again, is partially negatively charged, so it has an attraction to this hydrogen on another amine molecule or ammonia molecule, with this hydrogen being partially positively charged. So this hydrogen would be a donor, and this nitrogen would be an acceptor. And this is just the same thing, but with water. Again, the hydrogen will be partially positively charged, and nitrogen will be partially negatively charged. And remember that hydrogen bonds can only be a donor if a compound has an oxygen or nitrogen that's bonded to a hydrogen. They can still be acceptors if there's just an oxygen or nitrogen, but it has to be bonded to a hydrogen for it to be a donor. Also, along with amines, they're bases. They're both Bronsted and Lewis bases. So Bronsted bases just means it's a proton acceptor, so it can react with H+. Lewis bases mean it's a electron pair donor. So in other words, it's a nucleophile, so it can react with an electrophile and form a compound. Okay, so now onto alcohols. There's a few reactions you have to know for alcohols. First one is the reaction of alcohols with alkali metals, which, if you remember, forms an alkoxide. Okay, so in these reactions, basically all you're doing is replacing these hydrogens with the metal. Okay, and they just have to be any alkali metal, so it can be sodium, lithium, or potassium. So in this case, in these alcohols, these OH bonds, they're covalent, but when you replace that hydrogen with the metal, it becomes an ionic bond. So a negative charge forms on the oxygen with a positively charged metal. Okay? And then you also release one hydrogen, but you can't just write H, because hydrogen is only stable by itself in H2. So you have to write 1/2 H2, even though it's just one hydrogen. So same thing for this one. Okay, so you'll just replace that hydrogen with the metal, and you'll form an ionic bond. So again, a negative charge will form on that oxygen, and then the metal will have a positive charge. And then you'll also release your hydrogen. Okay? And the exact same thing here. Just replace the hydrogen with the metal, form an ionic bond. And these are all alkoxides, which you'll need to know for later reactions. We okay with that? Okay. So the next reaction for alcohols is dehydration. So the product for these reactions is the general equation is you'll take this OH group off and a hydrogen from an adjacent carbon and form a double bond in its place, and then release water. Okay? So the mechanism, our first step is going to be to protonate that OH group, because it's a poor leaving group right now, meaning that this bond can't be broken easily but we want to take that group off, so we need to convert it to a good leaving group. And I'm going to do that with my sulfuric acid, which is my catalyst. So, and if you don't remember, the structure of sulfuric acid is this. That's an H. And that's what I'm using to catalyze, okay? So I need to protonate this OH group. So one of these lone pairs of electrons from oxygen is going to come and take that hydrogen from sulfuric acid, and then this HO bond will break, and those bonding electrons will go to oxygen. So that forms OH2, and a positive charge forms on that oxygen. And then I have that anion that I made from sulfuric acid. Okay, so now this is a good leaving group because of that positive charge on that oxygen. That bond is strained, so it can come off easily. So this CO bond is going to break, and those bonding electrons will go to that positively charged oxygen. And I'll lose water. Okay. So now I have a carbocation where that water just came off. This is a secondary carbocation. So, and all of these carbons have two hydrogens, remember? So it's going to take one of these hydrogens, and it doesn't matter which one for now because all of these are equivalent. So this anion will take this hydrogen from an adjacent carbon to the positive charge. This CH bond will break, and those bonding electrons will go to reform that double bond and also neutralize that positive charge. Okay, and I also formed water in this step. And then right here, I reformed sulfuric acid, which is my catalyst. So I always have to reform my catalyst. Be good with dehydration?
So in the first step, is the oxygen from the OH relating electrons to hydrogen from sulfuric acid?
Yeah, to form an OH bond here. Okay? Yeah. So the electrons will go to the hydrogen to form an OH bond. Okay? So they don't necessarily go to the hydrogen, but they go in between the oxygen and hydrogen to form an OH bond.
That's like HOH.
Yeah, it's just water. That's why we can take it off, is because it's stable by itself. Okay. We good? Okay. So now Lucas reactions. Lucas reactions do not require a catalyst. These are a bit simpler in my opinion. So your product for Lucas reactions, you just replace the OH group with your halogen. And you also form water from your OH group and this hydrogen. Okay, we good now? I think we're good. It keeps turning off. I don't know why. I'm not touching it. So now I have a good leaving group. So water can come off, so this CO bond will break, and those electrons will go to that positively charged oxygen. So I'll lose water. And a carbocation will I'll just keep doing this because I don't want to go through that whole process. You feel me? Because I have something at 7, so I gotta go kind of fast. But yeah, so water will come off and a positive charge will form in this place to form a carbocation. This is again a secondary carbocation. And now I have this ion that I made from HI that's just going to come and attach at that positively charged carbon on the ring. So that's my product, and I also formed water back here for this step. Okay. Okay. So, phenols and phenoxides. So phenols are a class of organic compound, and it has an OH group that's connected to an aromatic ring. In other words, it's connected to an sp2 hybridized carbon. And phenols are not an alcohol because alcohols have an OH group connected to an sp3 hybridized carbon, and phenols have the OH group connected to sp2. So phenols are weakly acidic because of a conjugation effect. So if you remember in aromatic rings, all of these pi electrons are delocalized, okay? So, and this oxygen has 2 lone pairs of electrons. So what happens is these lone pair of electrons can actually delocalize to this ring, which will put a positive charge on that oxygen, which will weaken this OH bond. So that's why it's weakly acidic. And because that bond is weakened, it can break apart in water, at least partially. So here's that reaction. You have phenol in aqueous solution, so it's in water, and it can partially break apart to this and H+. So it's a weak acid. And because of that, it can have acid-base reactions with a strong base. So in this case, I have sodium hydroxide can react with a phenol to form this, which is a phenoxide. And if you remember from Chem 1, acid and base reactions always form a salt and water. So, and a salt just means an ionic compound. So this is just an acid-base reaction. So this looks similar to an alkoxide, but remember you make an alkoxide by reacting an alcohol with an alkali metal. So that would be just this to form this alkoxide from an alcohol, but to make a phenoxide, you have to react with the strong base. Okay, so you need this OH group to have an acid-base reaction since phenols are weakly acidic. So you'll need to remember that. Okay, so ethers. This is an ether right here. So ethers are just an oxygen with 2 alkyl groups on either side. They can be different, they can be the same. And you form ethers by reacting either an alkoxide or a phenoxide with a primary alkyl halide. And that forms an ether. Okay, so the general equation, and this could either be this could also be lithium or potassium, and this could be chlorine or iodine. So it doesn't matter what alkali metal or halogen you use, just that you have them there. So the general equation is you react an alkoxide or a phenoxide as well with a primary alkyl halide. Okay, so this halogen has to be connected to a carbon that's only connected to one other carbon, or it's just a methyl group. And this forms an ether, and then that alkali metal and the halogen will form an ionic compound. Okay, so this is similar to something you had on your homework. So he might give you a product and ask you how to make it, so he'll ask for the reactants. And how you do these, you just split it at the oxygen, and one side will be your alkoxide and the other side will be your alkyl halide. Okay, so in this case, I know this side has to be my alkyl halide, because if I made this side my alkyl halide, it would not be primary because this carbon is secondary. Okay, so that left side will be my alkoxide, okay, and then the other side will be my alkyl halide. Which will form that ether. Okay, does that make sense? Okay, and I normally always use sodium and bromine, but you don't have to. It doesn't matter which ones you use. That's just normally my go-to. And this does not require a catalyst either. Okay, so now we can move on to carbonyl compounds. So this is a carbonyl group. So you just have a carbon double bonded to an oxygen. Okay, and the bonding in these groups, a carbon-oxygen bond is polar. So, and oxygen is more electronegative than carbon, so it'll pull the electron density towards the oxygen. So this oxygen will be partially negatively charged, and this carbon will be partially positively charged. Okay, and this arrow means that it's polar with the electron density going towards the oxygen. So there's a few different carbonyl compounds. You can have an aldehyde, which this is your functional group for your aldehyde. You have the carbon double bonded to the oxygen, and you have to have a hydrogen on one side, and you can have a alkyl group on the other side or another hydrogen. You have ketones, so ketones have to have an alkyl group on either side. So the simplest one is acetone, which I promise he'll ask you what that is about 10 more times, and you have to know it or he'll get angry. But he won't get angry, but you need to know it. Make him proud. So, and carboxylic acids is another one. You have, again, the carbon double bonded to oxygen, but you have an OH group on the other side. So this is your functional group, and that is a carboxyl group. So a carboxyl group is a combination of a carbonyl group and then a hydroxyl group, which is that right there. And then you can have a hydrogen or an alkyl group on the other side. Okay, so with aldehydes and ketones and all that, they can undergo organic redox reactions. Okay, so organic redox reactions are a bit different from the redox reactions you learned in Chem 1. Just in definition, not really in principle, but the definition is a little bit different. So oxidation of organic compounds just means it either gains an oxygen or loses hydrogen. And reduction is the opposite. it loses oxygen or gains hydrogen. So in the case of primary alcohols, they can oxidize to an aldehyde, and an oxidant you can use is potassium permanganate. That's probably the only one you'll see, and you'll be expected to know that. That is potassium permanganate. And that is an oxidant. Okay, so that's just a compound used to oxidize. So from here to here, I lost one hydrogen from this middle carbon, and then that formed a double bond to that oxygen. So this formed an aldehyde because I have that hydrogen on that other side. And then if I keep reacting with potassium permanganate, I can gain another oxygen right in there and form a carboxylic acid. Okay, and then reduction is just the same exact thing but backwards. And instead of potassium permanganate, you could use tin in hydrochloric acid, which is probably the only reductant you'll be expected to know.
Is it both of those or just like one?
It's both. You have to use them together as one reducing agent.
Would you write it like that?
Yeah. So, if you use tin and hydrochloric acid, you can go backwards. So if you reacted this with carboxylic acid, you could go backwards to an aldehyde. Keep reacting, you can go backwards to a primary alcohol. And in the case of secondary alcohols, if you react with potassium permanganate, you can oxidize to a ketone. So the only thing I can do is get rid of this hydrogen and this one, and then it stops at a ketone. Okay, I can't oxidize that any further. And then I can also go backwards if I wanted to reduce it, so I could add hydrogens here and here, and then go backwards to a secondary alcohol. Make sense? Okay. So, carboxylic acids and carboxyl groups. Here's that carboxyl group I just told you about. So, very similar to phenols, carboxylic acids are also slightly acidic. And this is because of the same conjugation effect as phenols. Is this oxygen has those two lone pairs of electrons. So those lone pairs of electrons can actually move to this, this should be a double bond here, my bad, to this CO bond to form a double bond there. And then this CO double bond can move upwards and make an ion there. Okay, so that puts a positive charge on this oxygen, which weakens this OH bond. So again, in water, it can partially break apart. So that's this reaction right here. If you put a carboxylic acid in water in aqueous solution, it can partially dissociate into this compound and H+, which is called a carboxylate. You'll need to know that term at some point. And again, similar to phenols, carboxylic acids can undergo acid-base reactions. And again, that forms a salt and water. So it forms this ionic compound. Okay. All good? Okay, so from carboxylic acids, I can make an ester. So an ester, you have an alkyl group on one side and on the other side as well. And you have a carbon double bonded to an oxygen, and then that carbon is bonded to another oxygen. Okay, so this is kind of like a mix between an ether and a carboxyl group. Okay, so you can make esters from carboxylic acids and alcohols, and you have to catalyze with a strong acid. Okay, so here's one of those reactions. Basically, the general equation is you'll take the OH group from the carboxylic acid and a hydrogen from the alcohol, and then it'll be released as water. And then this will just form an ester bond over there. Okay? And this is an ester bond, that bond right there. Okay? And that forms this product. This is it in line structure, but I normally always put things in structural formula because I just find it easier, but it's up to you. Okay. And then I believe this is the last thing. This is the mechanism for these reactions for Fischer esterification, which these are a tiny bit tricky, but not too bad. So the product again is you'll take an OH group from the carboxylic acid, the hydrogen from the alcohol, and you'll just put them together. That will form this ester and also water. And I have to do this in acid. Okay. So my mechanism for this, I had to write this down because I don't quite remember this that well. It's okay. Okay. So carboxyl groups, as they are weak electrophiles because that carbon is partially positively charged. But if I wanted to react with an alcohol, which is a weak nucleophile, so weak electrophiles and weak nucleophiles do not react. One of them has to be strong. So what I'm going to do is I'm going to protonate that carbonyl oxygen to form a strong electrophile. Okay, which that proton will come from your strong acid. Okay, so those lone pair electrons from that carbonyl oxygen will come and take that hydrogen. Which will form a positive charge on that oxygen. Okay. And because of that positive charge, this carbon is now a strong electrophile. So now I can add an alcohol, which is a weak nucleophile. So it's electrophilic because that carbon is partially positively charged, but it's only partially positively charged, so that's why it's not a strong electrophile like a carbocation would be, because it doesn't have a full positive charge. Okay, so now I have my alcohol right here, and this oxygen has 2 lone pairs of electrons again. So now that this OH group is protonated, now I can add this alcohol here. So when these lone pair of electrons come here to form this bond, this CO double bond will break, and these bonding electrons will go to that oxygen to neutralize that positive charge. Okay, so I still have that hydrogen on this oxygen here, so this has a positive charge. So in this next step, it's called intermolecular hydrogen transfer. Okay, so And above that arrow, you'll write plus or minus H plus because you're just moving a hydrogen from already inside the molecule. So you'll move this hydrogen from that oxygen to this one right here. Okay, so that forms a positive charge on that one now. And now I have OH2, which is a good leaving group. So that's water. So now water can come off. So that CO bond will break. I'm running out of room. It's getting messy. I'm sorry. Okay. So when that water comes off, these lone pairs of electrons from that oxygen up there come down to form a double bond here. And this group can come up to here. So after this, that oxygen has a positive charge. And then I just have to deprotonate. So I'm just going to take off that hydrogen, and then that forms this product, which I ran out of room. And then that hydrogen ion will come off, which is what my catalyst was. So I reformed my catalyst, and then I also formed water. I know that's ugly, but does that make sense? Yeah, he skimmed over this in class. So you're probably not as familiar with this mechanism. It does get a tiny bit tricky, but that is I think it's the last slide in that section 3 PowerPoint. So go back and look at that if this looks crazy. Okay. And that was all I had. So if you have any questions, I have 9 minutes. Okay. Do I have the exam? No.
Not the exam, like the template.
What do you mean by template? Like a study guide?
No.
It's going to be about the, I believe it's still 9 questions like the last one. Other than that, I know what the one last year was like, and I think it's the same test. So I know vaguely what's going to be on it. But you also have that study guide in eLearn on that first page that'll tell you everything you're expected to know for the exam.
Are you able to send this out?
Mm-hmm. Yes, I will do that. If I don't get that up by tomorrow, somebody remind me, because I might forget.
Thank you.